Okay, in chapter 2, we're going to start looking at the chemistry of life, biology. And we're going to start at that lowest level of hierarchy, which is the atom, right? An element. So a chemical element is just the simplest, purest form of matter that has the unique properties of that matter. Often in biology, we will talk about trace elements, so things that the body needs. The reason they're called trace elements isn't because they aren't important or aren't very important. It's because we only need a little bit. So these are things like zinc and iron and iodine. Inorganic, so meaning non-living elements, are typically called minerals. So if we took an element and we cut it and we cut it and we cut it until we got the smallest particle that we could possibly get that still retains the same properties, it would be an atom. So this is a chemical kind of construction of what an atom looks like. An atom is made up of 3 subatomic particles. Sub meaning below, so subatomic is smaller than atom. We have protons. Protons have a positive charge. P for proton, P for positive. That's how I remember that one. Neutrons are neutral, so they do not have a charge. They are not positive and they are not negative. NEU for neutron, NEU for neutral, nu. And the third subatomic particle is the electron. The electrons are negative. I don't have a fancy way of remembering that one. I usually just write electrons like E negative to help me remember that they have a negative charge. So the way these are situated, inside of the nucleus, which is here in the center, we have the protons and the neutrons. So the nucleus here is very positive. And then outside of that, surrounding it, we have what are called electron shells. And we have these little electron particles that are negatively charged. And if you think about it, opposites attract. So positive and negative are attracted to each other. So that's what keeps the electrons surrounding this nucleus of the atom. Valence electrons are the most important electrons when we think about chemical reactions. So a valence electron is the outermost energy levels. These are the ones that are the farthest away from the center. And different atoms are going to have different numbers of electron shells. The outermost shell is the valence shell. So if you look at this molecule down here at the bottom, the outermost shell is this third layer, right? 1, 2, 3. This is my valence electrons. If we look at this molecule up here, it's only got 1, 2 shells for electrons. So that means the second one out here is my valence electron shell. These are just the outermost, and these are going to determine how this atom bonds to other chemicals. So normally, an atom will have the same number of protons and neutrons and electrons. The number of neutrons can actually change. So an isotope is a molecule with the same number of protons, meaning it's the same element, but it has a different number of neutrons. So this is hydrogen. Hydrogen has 1 proton right here, 1 proton. In this hydrogen, this is normal hydrogen, there's no neutrons. This hydrogen has 1 neutron, 0, 1, and then this one actually has 2 neutrons. So these are called isotopes, and they are relatively unstable. We have carbon isotopes, so we have carbon 12, carbon 14, carbon 16, and those are all different isotopes of carbon. So we use isotopes for radioactive dating, right? So if you've ever heard of carbon dating, we use these carbon isotopes for that. We also use them in biological processes. So a lot of times, if we're doing imaging, so CT scans, we will inject a person with an isotope. And when it sheds these unstable neutrons. It actually gives off radioactive energy. And that energy is what fluoresces under the machine, the imaging machine. An ion happens when we change the number of electrons. So in this example here, we have a sodium molecule and a chlorine molecule. Sodium's valence shell is this outermost shell, and if you look at it, it's only got one electron here. This outermost shell can actually hold 8 electrons. And then if you look at chlorine, this outermost shell has 7, so it's only missing 1. Typically, atoms are going to be happy when their valence shell is full. So in this case, we can make both of these happy by giving this electron to chlorine. Once this is gone, look down here, it doesn't have an outer shell anymore. This becomes the valence shell, and it's happy. And chlorine got its extra electron, and so now its valence shell is full, and it's happy too. So an ion is charged. Remember that protons have a positive charge, and electrons have a negative charge. So if the number of protons is equal to electrons, then we have no overall charge. But if I get rid of an electron, so I remove a negative, I'm going to end up with a positive charge, because now my protons are greater than the number of electrons. And if I gain an electron, right, I get a new electron, I'm going to end up with a negative charge, because now I have fewer protons than electrons. So this would be a positive ion, and then over here this chlorine would be a negative ion. A free radical is anything that has an odd number of electrons, meaning that they're not paired, right? So here we've got, these are paired, but this one is unpaired here, right? So this has got an odd number of electrons in its valence shell. Free radicals are very damaging to our body. And one way that we fight against free radicals in our body is antioxidants. So if you think about a food that's been marked as good because it's got lots of antioxidants in it, things like coffee, blueberries have really high levels of antioxidants. So an antioxidant, what it will do is it will donate an electron to that free radical, making it so it's not harmful. It's taking its teeth away, right? So instead of this free radical stealing an electron from your body and causing you cellular harm, it's going to take an electron from this antioxidant. And so that's going to help protect your body against the damage of free radicals. A molecule is made up of 2 or more atoms united by a bond. So when we have 2 or more different elements, we typically call this a compound. I'm not going to get too picky about that. I usually just call everything a molecule. 2 molecules with the same structure but different 3D shapes are called isomers. So ethanol and ethyl ether are called isomers. Please don't get isomers confused with isotope. Isotope was when they had different numbers of neutrons. So let's look at these 2 isomers. They both have the same chemical formula. Here's my chemical formula, C2H6O. So if we go to the structure and we count them, right, we have 1, 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. This molecule has the same numbers, 1, 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. But these structures are different. So if I had only written this, you wouldn't be able to tell the difference. But when you see the actual picture, you can tell that these are isomers because they have different structures. And if you remember what we said about structure, if we have a different structure, we're going to function differently. All right, a chemical bond is formed when electrons move, or when there's an association formed between two separate molecules. So we've already seen an example of an ionic bond. An ionic bond is when we take an electron and we're going to move it from one element to another one. What creates this bond is that we now have a positive anion and a negative ion. And these are going to be attracted to each other, creating an ionic bond. A covalent bond forms when two atoms are going to share an electron instead of transferring them. So this happens in hydrogen. So here's a hydrogen. It's got one proton and one electron. But this inner shell actually wants two electrons. So here's another hydrogen with one electron, one proton. Neither one of them will be satisfied if we just move one over. So instead, they're going to share both of them and create a covalent bond. A covalent bond can be polar or nonpolar. So when a covalent bond is nonpolar, like this example, the two hydrogens are going to share their two electrons equally. Think about two kids playing tug of war. They're the same size, same shape. They're going to pull and pull and pull, and the two electrons are going to be shared right in the middle between the two. Hydrogen and oxygen, this is a covalent bond here, they share electrons. But oxygen is really greedy. It likes electrons more than hydrogen does. Think about the same game of tug of war, only now we've got a little kid and like a teenager who's stronger, right? So oxygen is going to pull harder on the electrons, and the electrons are going to spend more time around oxygen than around hydrogen. So this would be polar or non-polar, up here. And this is an example of a polar hydrogen or a covalent bond. A hydrogen bond is a weak interaction between molecules. So this only happens with polar covalent bonds. So here's a water molecule with a polar covalent. Here's another water molecule with a polar covalent. This right here is a hydrogen bond. And this is a weak interaction between the oxygen of one water and the hydrogen of another water. Right? So this is the hydrogen bond because this oxygen, it's spending a lot of time with electrons, so it's going to be a little bit negative. And this hydrogen, it's not spending much time with its electrons, so it's going to be a little bit positive. And that creates this very weak electrical attraction. A van der Waals force is very similar to this, but it's even weaker. A van der Waals force is actually what helps a gecko's toe pads be able to climb a wall. So there's hundreds of thousands of teeny tiny hairs on these little toe pads, and they have tiny little brief interactions with the wall. And that's enough to be able to hold that gecko's body against a wall. So take a moment and reflect on covalent ionic bonding and the difference between polar and nonpolar bonds.